Thanks. Thanks very much, Noah. Wow, great crowd for 9 o'clock in the morning. I really appreciate it. So, I realized at some point this morning that I don't actually answer these two questions about in my talk, so I'll answer them now. Can global freshwater security exist, and can scientists communicate the challenge? And I think yes and no. I'll give you a neutral answer, and you'll see why. So, I mean, it can't exist because it has to exist. And can scientists communicate the challenge? Yes, because we have to. But they're both a challenge. So, I will talk about water security, just a very brief definition. It's a term that we hear quite a bit. And I'll focus mostly on the GRACE mission, as Noah said, in terms of what satellites are telling us about water availability. Then what are the implications? In a few slides that I think kind of spell out, not all of the implications, but some of the things that I've been thinking about. And I think they're all potential research projects and certainly collaboration. Noah mentioned that I moved to JPL a few years ago in 2014. And so I'll show you a couple of things that we've started there, some modeling and some stakeholder relations that we're building. And then what should we be doing as a community? And here, this is the challenge of communication. And I think it's a responsibility of us as scientists to do this communication, but it's not for everybody, and it absolutely has its pitfalls. And if we have time, or beer, or both, we can talk about what those pitfalls are. So defining water security. I use a very simple definition. And it's one that I wrote for a NASA proposal a few years ago. And when I reflect upon that definition and the outcome of the proposal, which was rejected, I realized that maybe it's not the best definition, but anyway, it's very simple. It's, can a region provide a reliable supply of potable water to a region to meet all of the competing uses? So water for food, water for energy, water for people, water for the and I changed up this. I forgot this. I changed up this picture when I gave a talk to the Salmon Restoration Federation, and so I had to throw that salmon in there. And the person before me, the title of her talk was "If Salmon Could Speak," and so I followed her, and I said, "If salmon could speak, this one would be saying, oh crap." So, water to grow food, water for the environment, water for people, water for energy production, right? Water for economic growth. These are all competing uses. So if a region can provide a reliable supply of potable water to meet those competing and various uses now and into the future, then we say that it's water secure, but that's becoming more and more of a challenge. The State Department now has a definition that includes aspects of terrorism. USGS has a definition that includes things like thinking about water management under changing extremes with more flooding and more drought. And so these are all things that we have to be thinking about. Okay, so the satellites, what are satellites telling us about water availability? Many of you know about GRACE, but for those of you who don't, it's kind of a cool mission. It was launched on St. Patrick's Day in 2002, so it's 15 years old. I'll show you some of the birthday cards, seriously, that we had for the birthday party. It orbits at about 400 kilometers, and the two satellites are separated by about 200 kilometers. They're not very big, right? You can tell from scale from this picture. I like to call it a scale in the sky, and I'll explain that in just a second. It measures changes in total water storage at monthly and longer time scales for regions that are 150,000 square kilometers and greater. So it's pretty low resolution in space and time. So it's not going to tell us about the soil moisture out here in some of these fields or on campus, but it is going to tell us about water storage changes, about the size, maybe of half the size of Colorado. So why is it, why do I call it a scale in the sky? Because these two, rather than being an optical satellite or a satellite that's measuring emissions from the surface, these two satellites are responding to mass variations on the ground. So they orbit, they follow each other in a polar orbit. So as they orbit around the Earth, when they encounter a region like the Rockies that has had a lot of snow, say over the winter, that region has gained water mass, right? It's gained water weight. And so therefore it exerts a slightly greater gravitational tug on the satellites and pulls them down just a little bit towards the surface. And likewise, when they fly over a region that's lost water, say California because of the drought and the Central Valley because of all the groundwater depletion, that region has lost water weight. So it exerts slightly less of a gravitational tug on the satellites, and they float a little bit higher in their orbit. So by keeping track of the ups and downs and the vertical positions, also important. The horizontal is also important. We're able to map out the regions of the world that are gaining or losing water mass on a monthly basis. And some of what we see, I have to say, is a little bit scary. Accuracy is 1.5 centimeters, equivalent water height, meaning if you have 1.5 centimeters spread over this area of about 150,000, 200,000 square kilometers, then you can sense that, or the change as long as it's greater than that. So that's kind of incredible when you think about these satellites that are up at 400 kilometers sensing this change that's centimeter and a half thickness. There is a follow-on which is called the follow-on to launch later this year or early. I can never keep track, but I think right now we're on track for December 2017, but maybe into January 2018. It'll be the same configuration that I told you about. We call it a climate continuation mission. So we'll keep getting these great measurements that some of the folks here work on sea level, ice sheets, and then we're doing a lot of work on the water side. Okay, so in terms of scale, I already told you the answer, sort of, if you were paying attention. How big is the state of Colorado? So we want to know, like, can we see what's happening in Colorado with Grace? Does anyone know, in terms of square kilometers, how big it is? That could be right. I don't know. There's your answer. It's about 270,000 square kilometers, so it's plenty big. And I went to Steve Neerham's Grace site, and so here's Colorado. Sorry, I can't tell the difference between all the lines. Right, here's Colorado, and then here's one of the grids for which there's some data. And so these ups and downs are showing the monthly variations in total water storage. So you're seeing like wet season, dry season, wet season, dry season. In this case, there's a little bit of a trend. Looks great, right? You're gaining water. Except when you go over to the next box, you're losing water. So this is the challenge for us, is to look around the world and understand what's happening, right? Maybe there's a lot of farming going on here. Who knows? Maybe all the snow has been lost in the mountains, and now you're off in the plains, and right here in the rain shadows. So this is the challenge in unraveling some of this information that we get. I'll get into this a little bit more. I mentioned the birthday cards. Wow, we actually had a nerd satellite birthday party on St. Patrick's Day, which we should have been drinking green beer. But instead, we were toasting to 15 years of Grace. And these are some of the slides that were put out about some of the Grace accomplishments. So 2 satellites, 137 miles apart. How many? 2.4 billion miles traveled. Ice loss measured, 3,400 gigatons. A gigaton is a cubic kilometer. From Greenland, and 1,550 and for Antarctica, and cumulative sea level rise of about 13 millimeters. And I get jealous as a hydrologist that they didn't do one for groundwater, so I did one myself. And so it just took some of our results and projected them forward. So same thing, groundwater depletion measured 300 trillion gallons, okay, from the mid-latitude aquifers. All of the aquifers in the dry parts of the country that are getting drier, and we're using our groundwater there because it's dry, so we rely on groundwater, and we're depleting those aquifers, and they're all listed here, and I think I have a sea level equivalent as well, 3.15 millimeter contribution to sea level rise. Here's a recent animation we did. I'm not thrilled about this one, but it's one of the newest ones. It's for California. We had a congressman coming through, and so we rushed to do some new animation. So really the point is I want you to understand that we spend most of our time just looking at movies at JPL. And no, that's not true. But what I'm going to show you is animation of some of the GRACE data. We're going to see the ups and downs. We're going to focus on California. So it's going to be, when it's blue, there's more water. When there's red, there's less water. And we're going to go through the sort of GRACE history, which corresponds to a couple of phases of drought. So we're going to see from about 2000 to 2002, 2006, we're going to see a little increase. And then from about 2006 to 2010, we're going to see a decrease. And we have a little mini El Nino around 2010. Then we go into the really devastating last few years of drought. And so right around 2015 will be like, the screen should be covered in red. And then we get into this sort of incredible recovery that's, overtopping dams and, having people basically running away from the flooding. This goes by kind of quick. So here we go. So we're about to start this first phase of drought, 2006 through 2010. So things are getting a little bit red. And then around 2010, we get into this little mini El Nino, and we get a little recovery. And then all heck breaks loose. And right around 2015, things get pretty darn scary right there. And then we get into this, and then we get into this recovery, which, we've actually gone from the driest conditions, I'll show you on this next slide, driest conditions ever recorded to really the wettest conditions ever recorded. So from a water management perspective, that's pretty crazy. And also, as scientists, we're able to now sort of measure this and quantify this in ways that we haven't been able to do before. So, by the way, I'm going to start with California and then move to the Colorado River Basin and the globe, and we'll have a good cry, and then we'll talk a little bit about communication. So we're going to focus in this slide on the Sacramento, San Joaquin, and Tulare Lake Basin. This is where all the water is in California. And the blue is the Central Valley. Chances are, if you had any fruit or produce this morning, might have, well, no, these days we're doing a lot more local sourcing. So I'm sure at my restaurant, the oatmeal came from Gun Barrel or something. But about 90% of the produce that we eat in the country comes from the Central Valley. So here's another one of these GRACE time series. So wet season, dry season, wet season, dry season. We'll look at the changes in the total amount of water. So all of the soil, moisture, surface water, snow, groundwater. And so, we can see some oscillations there. And looking at some of these outtakes from the animation, we can see the dry seasons getting drier. And here's the, I'm supposed to have 2015 on there. Might have gotten left out. We can see these different time scales of drought. And so the recent drought, 2011 or 12 to 2015. So now we can say, hey, looks like this is when the drought ended. Kind of a difficult question to answer. So we can quantify, California lost 15 cubic kilometers of water per year. About 2/3 of that was groundwater. But, maybe this time period here, maybe this drought period actually went back to 2006. We can see that now from the GRACE data. Really, between 2002 and 2015, we're pretty much continuously losing water. A lot of that comes from groundwater. I'll show you that in a little bit. Then we've got this great recovery, okay? And so, does this suggest that we should stop conserving water and everything is fine? And that's what, in terms of communication, that's what the public would like to do. But the fact is that we still, in spite of this, we still have this tremendous groundwater depletion. So this is probably just a modest uptick in long term. I'll show you a 50-year groundwater slide in just a few slides. Oh, there's 2015. Sorry, I got out of order. Okay, so this is a slide from NOAA. These are some images from NOAA. So this recovery here, what happened? Well, one of the big things that happened was, it started raining, it started snowing, and these are some images from a press release that Noah Molach did, and so we're looking at snow cover in the Sierras in 2015, sort of, the year in which the drought really hit rock bottom, to 2017, and so the colors there represent more snow water, so the spatial extent, and then the greens and the blues represent more snow. So a lot of what's happened is happening on the surface. A lot of what's not happening is happening underground in terms of replenishment, and that's the groundwater. And so a big part of the message of what we've been able to uncover with GRACE, literally sort of uncover, is what's happening beneath the ground. And again, uniquely provided by a mission like GRACE, which, because it's not looking at emissions from the surface or optical images of the surface, we're sensing this total mass change. We're able to, quote unquote, see some of this activity that's happening underground. Hey, I put this in here because I'm sure there's at least one person in the audience that doesn't know what groundwater is, so don't mean to offend anyone. But groundwater is the water that is stored underground in aquifers, which are these soil and rock units that have porosity and so can store water. It's the primary water source for over 2 billion people worldwide, provides about half of the water that we use for irrigation. So, right, we rely on it quite heavily. In many cases, it's non-renewable, especially in these lower, we call these confined aquifers, because, it took thousands and thousands and tens of thousands of years for this water to accumulate in these aquifers, and we are literally burning through it in, on a decadal and century timescales. How do we get at this, these groundwater storage changes from GRACE? Well, GRACE is telling us the change. This is what GRACE tells us. The change in total water storage in a big area. That's equal to the change in the snow and the surface water and the soil moisture and the groundwater. So this is why we need to march for science, so people know that we can do algebra. If we rearrange this, can we solve for the change in groundwater storage if we have this information? Well, this now we have from GRACE. We never had it before. Again, it's for big areas, big aquifers, big groundwater basins, big river basins. But we need to get that other information, right? And so we've done a gazillion of these applications, and we use what we can, where we can use it. So if we're in California, we've got great data. We can get snow from people like NOAA, from the state, from the snow pillows, from the Weather Service. We can get we have measurements of the water in the rivers and in the reservoirs. Soil moisture is always kind of a challenge. Often we take it from computer models, but we are doing a better job with remote sensing these days, and even building up some soil moisture networks. So in short, if we want to estimate the groundwater, we want to isolate the blue stuff there at the bottom, the groundwater, then we have to subtract from the GRACE signal the snow, the surface water, and the soil moisture to get the residual groundwater signal. Just a little NASA advertisement. In the future, we're really pushing towards doing this all by satellite. So we've got the GRACE follow-on for total water storage. We've seen some of Noah Molach's work in snow. My colleague Tom Painter flies around in planes and does very high resolution measurements of snow water equivalent. SWAT, surface water and ocean topography, coming online in 2020. And the SMAP mission gets soil moisture now. So we're hoping in the future to do as much of this by remote sensing as we possibly can. All right, bottom line, we're in trouble with groundwater. This is a chart that combines USGS data shown in red, GRACE, our GRACE estimates of groundwater shown in green, goes back to 1962. Okay, really the full chart goes back to about 1935. So you can imagine this continuing back to 1935. Colors in the background represent whether it's a very wet period, shown in dark blue, or a dry period, shown in tan, or sort of in between the light tan, light blue, moderately wet, moderately dry. So there's a message here. One, groundwater, we're burning it up. Okay. Uh, average water table in the Central Valley is 2,500 feet deep. To dig a well that deep costs $250,000. There's a 1 to 2 year wait. Streams are going dry, ground is subsiding, as I'll show you in some of the next slides. So this is certainly not sustainable. So the other message is, even in the very wet periods, like the early 80s and the mid 90s, and probably we'll see what this wet period we've had now, we only get a little bit of an uptick, okay? So this idea that we're somehow going to replenish our aquifers, that's not going to happen because we use so much water to grow food, and a lot of it comes from, comes from the aquifers. So our history is big decline, little uptick, right, in a wet period, big decline, little uptick. Right? So we can expect a modest uptick, and we're working on characterizing what that uptick might look like. Yeah?
What percentage loss is it?
Of the total? No one knows. This is the problem, right? Seemingly. Yeah, okay. So here's, I wasn't going to talk about this today, but I'll throw it in here right now. One of the biggest problems we have is that we have not done the exploration that we need to do to understand how much groundwater we actually have. Okay, we've never done it because water doesn't have the appropriate value, or we haven't had to. Population hasn't been as great. The need to grow food hasn't been as great. We haven't been concerned until recently about climate change. We wrote 2 papers in 2015, one about global aquifers. I'll show you what are the slides, and the stress on the aquifers. The other was, what do we really know about the volume of water in the aquifers? The answer is startlingly uncertain and deeply concerning. So this gets to communication. I mean, getting that message out is quite a challenge. Now, that being said, we're past sort of the sustainability tipping points in that ground is sinking, as I'll show you, right? The streams are going dry. No one can afford the water. People now can't, are drinking bottled water because they can't afford to dig a deeper well. So we're sort of past, and the quality of the water degrades as you go deeper and deeper. So this is a huge issue. Yeah, but don't let that fool you, seriously, right? I mean, there have been a number of papers now that have been recently, right? So don't think like, oh, okay, yeah, it's no problem. It's a huge problem, okay? The ground is sinking. How much? Between 1925 and 1977, it sunk that much, okay? The streams are dry. If you drive around in the southern half of the state, there is no water in the rivers, right? The place is burning up. And the quality is just literally in the toilet. I was thinking about some good, funny recycling thing, but I can't. Not coming to me. I'll work on it though. But the quality of the water is degrading significantly. So now, it's at the point where it's not worth, the current water prices, not worth pumping it up in some places, and the area over which that's becoming increasingly true is increasing. Okay? So we're past what we would consider sustainability tipping points. Here's some charts on the subsidence. We're looking at this area here, shown in the box, so just east of the Bay Area. And these are some slides from my colleague Tom Farr. These are radar. These are not GRACE data. And so we're looking in the first phase of the California drought, 2007 to 2011, and then sort of peak drought. So we're looking at subsidence rates here. So what is subsidence? It's the ground sinking, right? I use the analogy, it's like a tire. Deflates like letting the air out of a tire, right? Just like you let the air out of the tire flattens out. When you pull water out of some aquifers, those that have a lot of clay minerals, they flatten out too, right? Because the water is actually supporting the mineral matrix. So in California, we're currently experiencing the fastest rates ever, and there's, of course, anything that's on top of this, like roads and, ironically, aqueducts and bridges and canals and so on, right, are at risk. So in the upper figure, we're looking at rates of a couple of inches per year to maybe a foot per year. And now here, peak drought, we're looking at rates that are up to a foot to a foot and a half per year. Okay, this was in 2014. The updates in 2015 and 2016, some of these hot spots are up to a meter per year. So it's more like 2 feet per year, right, to a meter per year. So think about that. It's not all over the Central Valley. It's confined to these places that have a lot of clay. But it is about 25%, the southeastern part of the valley, the southeastern sort of quadrant of the Central Valley. That's where all the clay is. So that's the part that's most at risk. Ironically, of course, this is where we want to put the high-speed train line right through there, right? This is a famous picture, right? I showed it before. This guy's name is Joe Poland. So USGS scientists took this picture in 1977. And so we photoshopped him to 2015, right? So we went from there to there, okay? So it's a problem. Okay, let's talk about the rest of the world. A little of both, but mostly the pumping. Yeah. Oh, it's mostly the pumping. The rain hasn't. I mean, those places. That part of California is dry, so the decreases are. It's already dry. The decreases haven't been that bad. And now we're at the point actually where we can fly aircraft radar and actually see, like, okay, which are the actual wells that are doing the pumping, and, right? So this was the stuff I showed you was a little bit coarser scale. So now we're at the point of being able to identify the sort of offending, the highest volume withdrawal wells. Okay, Colorado River Basin. So we wanted to understand what was going on in the basin, having this experience in California, right? And understanding that there's so much attention paid to surface water and management of surface water, but very little attention paid to managing groundwater. Now, we did just get groundwater legislation in California, but it's going to take another 25 years to fully implement. Well, this is common. It's common in the United States. It's common all over the world, right? That we pay a lot of attention to surface water. Colorado River Basin is very true, right? So we're always looking at Lake Powell, we're looking at Lake Mead, and we're looking at the bathtub ring, and that's great. We should do that, right? Because it's a great visual cue about the drought. But we wanted to understand what was the sort of, given that we see this from Grace, this is the time series for the basin from about 2005 through 2014. So we see the seasonal variations, but a trend. Where's that trend coming from? Is it coming from surface water? Is it coming from groundwater? Okay. And so that's what we did here. So we, combined all of our data sets and compared them to observations and made sure that they all made sense and that the Grace water storage signal matches the observations, and then bang, we get this. What does this tell us? This tells us what's happening in Lake Powell and Lake Mead, right? And this tells us what's happening with the groundwater. So while we're paying so much attention in managing the surface water, the groundwater is quietly disappearing, and it's disappearing at a rate of about 6 or 7 to 1. Yet, as many of you know, we don't really talk about in any of our basin discussions, right? We don't really talk about groundwater. Groundwater is really dealt with on a state-by-state basis. So now we're moving toward the tiers part of the but I said it with a smile, of the presentation. So here's the United States. So this is a trend map. So now we're looking at over the Grace time period, the places in the United States that are gaining water are shown in blue, and the places that are losing water are shown in red. Okay, so we see that the upper half of the country is getting wetter, and the lower half of the country is getting drier. We see that these are, well, I'll tell you, these are our two big food-producing regions. This is the southern Ogallala Aquifer, where we grow all of our grains, and here's the Central Valley, where we grow all of our produce. Okay. This is Alaskan glaciers melting up here. Okay, so this points to a problem. Now let's look at some animations of India and the Middle East. These are two places that also have a tremendous amount of groundwater depletion. And so the creeping red in both cases means progressively more water loss, and in these cases it's mostly groundwater loss. And issues here, what's happening in Syria, many people have tied to the drought and lack of water and lack of water security in the region, so that lack of commitment to providing water. So that's not great. And so here's the global story. So same map, right? So now the whole world, and the places that are losing the most water are the ice sheets, Greenland and Antarctica. I don't work on that, but colleagues like Steve Narum have been involved in looking at contributions to sea level rise. And likewise, the alpine glaciers, so Alaska, Patagonia. You can see some of the Colombian glaciers and the Peruvian glaciers starting to show up, and so they're melting away. But a lot of these other red spots are actually tied to aquifers. So the Central Valley, the High Plains, the Middle East, northwestern India, North China Plain, the Pilbara region in Australia, northwestern Australia, and the Hardy Aquifer in South America. So we know that they are tied to aquifers because we've just mapped this to this, right? We took the GRACE data and mapped it to these templates, and this is one of the papers that I talked about, one of these 2015 papers, where this was one paper, and the other paper was, well, can we answer that question of how much water is there? And the answer is no, and so most of the press was on, this is crazy, right? This is half of the, if you want to answer the sustainability question, one of the questions is, okay, what rate are you using it? And the other is, well, how much is there? Because if it's huge and it's not going to make a difference, it's no problem. And we know that it's a problem because it's making a difference, but we don't know the volume in many cases. So anyway, long story short, over half of the world's major aquifers are being depleted, right? We are past sustainability tipping points in the classic resource definition, which is we're mining it, we're using it faster than it's being replenished. And most of those aquifers in the mid-latitudes, most of those red ones, are tied to the major food-producing regions of the world, right? So, next phase for us, I think, needs to be communication. There's a climate change part to this as well. And for many of you who look at the IPCC data, know that climate models suggest that the wet parts of the world will get wetter, so the high latitudes in the tropics, and the dry parts of the world will get drier. This is an early IPCC figure showing the changes in precipitation by the end of the century, showing the high latitudes and the low latitudes getting wetter and the mid latitudes getting drier. And so I would, used to ask, are we seeing this in the GRACE data? And we finally just wrote the paper, and the answer is yes, we're seeing this in the GRACE data. And these are the trends for all of the red areas after we pull out the aquifers. This is the background, right? Dry areas getting drier, and the wet areas getting wetter. So this was a 2016 paper. So is it climate change? Well, it'll take a lot more data to find out, but it is consistent with the IPCC pattern. Wow, I'm depressing myself. What are the what are the implications? I didn't actually say that, but I didn't object to the cover, OC Weekly. We could go on and on about the implications. Let me just talk about some of the things that I've been thinking about. Most of the food-producing regions of the world are in a state of chronic water scarcity, and that's true for California, and it's true for the southern high plains. So, the drought comes and goes, and it sort of exposes this problem. That's really what happened in California, but California's problems are certainly not over. And it's primarily due to all the water that we use in the food industry, right, to grow food, and it's really important for people to understand that. So this is communication, right? If we're going to grow food, we probably need to do it, we do need to do it much more efficiently and sustainably. And especially now that we're growing so much weed, this is actually a huge issue in California. Seriously, I'm not kidding. This is a huge issue, right? So we just legalized it, and so the issues of water availability and water quality are now front and center. There are a lot of solutions for metropolitan regions, but fewer for agriculture. Okay? It just uses too much water. So, you know, we talk about desalination on the West Coast, and of course sewage recycling. All these are great, but it's not enough water to grow food. Okay? So agricultural, conservation, efficiency, pricing, innovation, on and on. Okay? This is what we need to do. I think this is a big part of our future. Either we need to move water to the food-producing regions, right, like the Central Valley or the Southern High Plains, or we move the food production to the places where the water is. Or some combination. That's, I think, just the reality, especially when, you know, we're at the point where the water is not really worth pulling out of the ground anymore. So I think that's a big part of our future, maybe 50 or 100 years from now. We have new groundwater legislation in California, and it's great that we have it, but it will take over 2 decades to implement. So food production, due to water scarcity, major global problem, needs our immediate attention. Another thing for us to think about, think about that national map I showed you about the U.S. We tend to think of our water problems as regional problems. Oh, it's California's problem. Oh, it's the Texas Panhandle problem, or it's the Oklahoma or the Kansas problem. It's not really, because this is how we grow food. So we grow food for the nation, but we use just water from that region. And so we have to think about that, whether that means, we just have to value it properly. I don't necessarily think we're going to be moving water around, but we might, my sort of science fiction dreams or nightmares involve desalination plants. And, if I wanted to write, has anyone read The Water Knife? Good book about sort of post-apocalyptic Colorado River basin when there's no water. So if I were going to write a book like that, it would be desal plants up and down the coast and pipelines moving water all around, because that's the sort of extreme future if we don't take action. And a lot of societal implications. Again, we could go on and on this. We're living in an era of rapid climate change, and with it, major changes in the water cycle. That big recovery I showed you at the end of the California Grace time series, from the driest ever to the wettest ever, right? That's a management nightmare, right? So there's major changes happening in the water cycle. I'm not sure we're really prepared for it. I don't think we're really ready for the water and the food and the energy future that some of those figures suggest, okay? Because they suggest things like haves and have-nots, right? This is the wet areas getting wetter and the dry areas getting drier. So what are we going to do? Are we going to move? I don't see us being a very mobile society today, right? So we're going to have the haves and the have-nots. And also, if you're within a region, but the water table's dropping, and you don't have $300,000 to dig a 3,000-foot well, you're not going to have water. So that's happening. Okay, this isn't fiction, right? This is happening. So are we prepared to address the inequities, the potential for violent conflict, and climate refugees? Water law, of course, most of it was put into place back when we were actually firing muskets at each other. So it's been a while, and when we didn't really understand how the water cycle worked and how interconnected it is. And even the need for international, transboundary, legal infrastructure, right? Agreements that include groundwater, better water sharing agreements, and even the civil infrastructure. If we're actually going to share water, say across, a simple example for the United States, not so for Canada, is sharing across the U.S.-Canadian border. I mean, can we do that? Just a little bit about what we're doing at JPL. We've got a bunch of missions, and NISAR, the radar mission, eco-stresses of evapotranspiration, and so on. And so one of our perspectives in moving there was that we really need to integrate this stuff together. And I know there's some similar efforts going on here at CU with modeling, with big data, with data integration. So arguably it's time to integrate these data into models. And so we fired up this thing called the Western States Water Mission, which is basically a very high resolution data integration platform, data assimilation platform of the flagship missions for the Western United States, 3 kilometers squared or less. That's because that's the scale of the tiny watersheds. We're doing it in a flight project framework, which means, it's moving pretty quickly. It's high priority. We're trying to represent the major features of the natural water cycle, but importantly, the managed water cycle, so conveyance, groundwater pumping, irrigation. We're hoping to provide NASA's best available estimates of freshwater availability in the western U.S. and linked to food production, energy production, agriculture. So the framework is this, and so we're modeling at about this scale. Here's the rivers. You can't really see them that well. This would be the dream if we could actually add on a floodplain hydraulic model to go from the scale at which this is the 3 kilometer scale, to the floodplain scale. We're not here, so we're here. We're operating in this space. So just to give you a sense of the 3 kilometer scale, if you've been to JPL, so this is a sort of 3 kilometer watershed that we're modeling. Oh, here it is here. So this is the one that JPL is in. So it goes like this, right? So here's JPL, here's the arroyo. Okay, so that's the scale at which we're trying to provide useful information. So integrated, so a decision maker could go in there and figure out, probably do it every week. Right now we're targeting monthly, but what the soil moisture is, what the water storage is, click on the rivers, get the stream flow. Right, so it's a sort of a high-resolution version of this, if some of you have heard about the National Water Model. This is a simulation of the rivers in California. So the blue doesn't mean inundation. The blue means higher river flow. So you can see the water coming off the mountains and flowing into the valley. And this is a similar one. So this is just, the resolution on the other one was so coarse that we just thinned it out to show you now we're simulating the whole western U.S. So we just did a couple of years and looked at only the major rivers. So we're simulating the whole western U.S., doing the surface water, the groundwater, all the fluxes, right, at this 3 kilometer resolution. In the interest of time, I'll skip over that. But, just to say, it's not all about just building the models. So we want to understand some of the integrated science. And this is a study that my colleague Min-Kui Lo and I did before he moved to National Taiwan University. And so we did a climate model study. And we looked at, if you have a detailed model like this that includes irrigation in the Central Valley in ways that models don't do it right now, what happens to that water? What sort of climate impact is it having when you put all this irrigation, pull water out from under the ground, put it on the surface, it evaporates, where does it go? How much goes back to the ocean and contributes to sea level rise? How much gets taken up by the atmosphere? What happens to it? In this case, in this time period that we studied, the irrigation water from the Central Valley travels eastward, hits the first big hotspot of water cycle activity, which is the Four Corners monsoon region, and literally strengthens the monsoon, right? Because water vapor is a powerful greenhouse gas, so it strengthens the monsoon. So the upward fluxes, the downward fluxes are increasing, actually increases stream flow back into the Colorado River. So this is in model space. Increases stream flow back into the Colorado River basin, which then we have this sort of crazy anthropogenic water cycle loop because that water goes into Lake Mead and then we put it in canals and send it back into California. Another thing that might be of interest is this Western Water Applications Office. It's actually a NASA-wide office, but it's housed at JPL. And it's a new initiative to, long story short, we're trying to connect stakeholder needs to NASA capabilities in water. Okay? We don't have a ton of money. We have a couple $1 million a year. We're trying to selectively pick projects where we can connect directly to stakeholders. So like the Department of Water Resources, for example, in California has been a big target. And this is a fallow land project that we're supporting. Some of you know I mentioned Tom Painter's ASO is another project that we're supporting. So we're figuring this out as we go. But of course, societal relevance and justifying the work that we do these days, and having people stakeholders actually use our data and use our research, right, is becoming more and more important. What should we be doing as a community? Communication. I don't have an answer. I just have a lot of thoughts, okay? And so do you, apparently. So this was on the cover of the Boulder Weekly. And so look, if we don't do anything as a community, there will be this sort of dark cloud over science and earth science. And, I'm not sure what that figure actually means, but I liked it. Put it on there. Anyway, okay, so I scribbled down some ideas yesterday. I went to this cool coffee shop. Was it Ozo? I was in there. Maybe some of you were there. And this came from a conversation. So actually leading a task force, Hari is on it, and for AGU hydrology, trying to figure out what the hydrology section should do. And we had some conversations. And look, so before we actually read some of these, communication is really, really important, right? I mean, communicating the work that we do and the importance of the work that we do is very important. Whether we're talking about to stakeholders, to donors, to elected officials, to water managers, to the general public, right? Whatever your target is, it's important. So this is more about what is your target. Okay? We don't want to just grab the bullhorn, right? We want to know like where we're going to point it and maybe how big it should be. So I do think we probably all need to become. So what are our goals? Well, we probably all need to become better communicators, right? So these are all valid, right? Do we want to bring attention to our university? Do we want to inform society? Do we want to bridge the gap between research and operations, right? Do we want to educate? Do we want to affect policy? Do we want to raise awareness of some central questions like, hey, we don't know how much water we have in our aquifers. This is the problem, right? Who are our targets? Is it internal? Is it internal within our professional society or within our university? Water managers, program managers, public, right? State and federal agencies and elected officials. And then what's the message? What is it that we're trying to communicate? Okay? Is it your soundbite? Hey, we have this center and we do this. Is it some new finding or some new method? Is it some big paper? Or do you just, want to let people know when it comes to maybe philanthropy or state officials that you're looking for their support for your research, that you just want to let them know what you do and why it's important. So these are all things that need to be part of a discussion so that you can have a strategy. So for me, in my experience, at first when I was at UCI, we had a center, and we wanted to do two things. We wanted to educate officials, and we wanted to get money. And so we had very clear targets. Right? And at JPL, it's become a little bit different for me personally. It's been more about educating the public about some of the stuff that I told you today, mainly the disappearance of it. Okay? So I want to show you a few more things, show you a little film clip, and then we'll be done. Some closing thoughts. There is absolutely no substitute for high-quality, peer-reviewed research, right? This is who we are. So without that, we have nothing to communicate, all right? So let's all keep that in mind. Then, if you choose to take the extra step, have some concise goals, get some training, work with experienced communicators. Maybe you have faculty colleagues that are good at it. Develop a strategy and build experience. I mean, my experience has mostly been sort of feet to the fire. And it's worked out okay. In my opinion, I think that we need to engage the public. I think we need to do this. We need to engage decision makers and elected officials. So we can talk about whether it's a responsibility or a nuisance. I think it's a responsibility. This raises issues for our young people. Are they going to get credit for writing a very impactful opinion piece versus another paper in water resources research? I can say without hesitation that my most impactful writing has been in the Los Angeles Times, not in even a science or a nature paper. So if students that might be out there, if you are interested, you should push your supervisors to get involved. That's how I got involved. It was through my students. We have an issue in hydrology, and that is, we're pretty scattered over different sub-areas of hydrology. We don't rally around big questions like how fast are the ice sheets melting? How fast is sea level rising? We don't do that, and so it's a problem. So I think we need to focus on, so I'm so glad you asked that question about the aquifer. We need to focus around certain questions like, we don't know how much fresh water we have. That seems like a pretty good question. And then consistent, clear, and targeted messaging are essential. The food industry, let me get back to this. This is where all the water goes, and we hardly ever talk about it. All the water, right? 80% of the water. So we're probably going nowhere in terms of long-term sustainability unless we get the food industry on board. Now, they're very interested. Just up to us to find, which companies among many are very interested. Some of them have, very active in sustainability, so they understand. Okay, so I just want to close with a little film clip. I used to think this, right, as a professor, right? Once people really understand the source of their water and how it's changing, then they'll really accept the need for change, the need for management, right? The need for action, protection. So in other words, like, in California, I used to think, well, if we tell people that their water comes from, and they understand that their water comes from the snowpack, here it is, like, a lot of snow, no snow, although this year is a bad example. But, in general, the snowpack is decreasing. Groundwater is disappearing, right? Surface water is disappearing. These are our major sources of water, right? The snow, Colorado River Basin, and groundwater. If you understand how those are changing, right, you would think that that could make a difference in people's thinking. Well, in terms of communication, I was encouraged very early on. This is I'm going to show you a clip. Noah mentioned Last Call at the Oasis. This is a clip from Last Call at the Oasis. I was encouraged by a congresswoman to go to Fresno, talk to farmers, tell them this stuff here on the upper right. Tell them what you're seeing with the GRACE data. So they'll understand that the groundwater is disappearing. And you really need to go reach out to them, and they're going to understand. Okay? So let's see if that actually happened.
Let me be abundantly clear about this. California faces a water crisis of potentially epic proportions. How we respond today will define who we are tomorrow. Here locally, need additional storage. They built reservoirs for a reason. Shasta, Stewart.
You go to the bank, county taxes, you're going to try to farm as much as you can.
They're not going to make more water. The only solution to this thing is conservation.
I agree we should look into conservation, but that's not going to yield or have any effect on our groundwater shortage.
I didn't want to get into this, but your arguments about conservation efficiency are just wrong. And if you're right, the conservation and efficiency isn't going to get us anything. And if I'm right that there's not a lot of new supply out there, then what are we left with? Take land out of production. I don't know anyone who wants that.
Your arguments just don't make any sense. You have to live in how we understand management of water here.
And you're one manager.
Well, now of epic proportions, and I said that. And I'm not sure that it really resonated, which to me is a little startling. We talk about water. We need a plan, and we don't have one, and it is complex. We're screwed.
So obviously it doesn't always go well, and I have several other examples of how it always doesn't go the way that you think it's going to go, but you know, we really do. As a community, we really need to work together to elevate critical water issues to the level of everyday understanding. Thank you.